just doesn't happen. All right. What's up, Lilster? 18? Sure. So here we're asked to do some long division. So I would also point out to the way 18 is currently written that you couldn't do the synthetic division on it if you had wanted to. Thanks, Megs. Hold on a second. He's absent. Yeah, you're welcome. Peyton, this is for you. Since that divisor doesn't have leading coefficient of 1, now there's ways you can kind of get around the leading coefficient thing, but it can be kind of a hassle. So, and now I notice when I'm writing the divisor and I have x cubes, but I don't have any x squareds. So I'm going to put a 0x squared there. Now, if you didn't put that piece in, it would be okay because it's still recoverable, but you have to be real careful about how you're lining things up and making sure you're only combining like terms. I think it's massively easier to remember to put the 0 in there. All right. So let's start. We ask ourselves, what times 2x gives us x cubed? So I know that 1/2 times 2 is going to get to the coefficient of 1. And then x squared times x will get us to the coefficient of, or get the exponent of 3. So that'll give me my x cubed. And when I multiply that to the -4, that gives me -2x squared. And we subtract out. Okay. I like to, rather than think about this as a subtraction problem, I like to think about it as an addition problem where I've distributed the negative. So I distribute the negative onto there and then onto there. So x cubed plus a negative x cubed, those just cancel out. 0x squared plus 2x squared gives me 2x squared. And then I'll bring the rest of this thing down. And we'll ask then, what times 2x gives me 2x squared? X. So I'll write plus x up top. And then I'll distribute this to both terms of my divisor. And we'll subtract down. Again, I'm going to distribute the negative. So 2x squared minus 2x squared, again, those just cancel out. -7x plus 4x is -3x. And then we'll bring everything else down. We're on to the last step. So we're going to ask ourselves, what times 2x gives us -3x? Oh, boysy. Well, 3/2, when I multiply that to 2, is going to give me 6/2, which reduces down to 3. So again, distribute that through. So I have -3x, and then -3/2 times -4 gives me positive 12/2, which is just 6. We'll distribute the negative through, so that becomes positive. That becomes negative. -3x plus 3x cancel out. 1 plus -6 is -5. So the way we'd write our final answer would be 1/2 x squared plus x minus 3/2. That's my quotient, plus my remainder, which is -5, over my divisor, which is 2x minus 4. So that's the form for our final answer. Is that okay, Lily? There was some kind of sneaky fraction things that happened in there that you had to be okay with, but that's okay. I mean, it doesn't seem obvious that you'd want to use a fraction for a coefficient, but you can. And in cases like this, you know, we had to. Peyton? Sure. Let's see. So 10, it says, asks us to find those zeros there algebraically. Okay. Oops. So to find zeros, basically, I'm just going to be replacing the g of x with a 0 and then solving. So if I'm solving a polynomial algebraically, the first thing I'd want to do is look for a leading coefficient, or I'm sorry, greatest common factor. There is none, right? So there's nothing in common between 2, 1, and 3, and then there's x or x squared, x and a constant, so there's no greatest common factor. Okay, so nothing to do there. Next thing we'll do is look at the number of terms. Here we have 3 terms. With a polynomial with 3 terms, we'd want to check to see if it's in the quadratic form. This one not only is in the quadratic form, it's just quadratic. So we're good there. To determine what we want to do with the quadratic, we want to check to see the leading coefficient. Here we notice the leading coefficient is 1, or is not 1. So here it means we have to do that longer kind of factoring. So here the question we need to answer, at least for starters, is to find the 2 numbers that multiply to give us the leading coefficient times the constant term, and then add to give us the coefficient on that linear term. So the 2 numbers that multiply to give us -6 and add to give us +1 are -2 and +3. Good. Now what we do with that is we can't go straight to the factored form with that information. That doesn't tell us how to factor that exactly. What it does is it tells us how to break up that linear term in the middle. So the x in the middle I'm going to rewrite as -x plus 3x. So that's where I'm using the -2 and the 3, is it tells me how to break up that x term in the middle. Is that okay? Now I'm going to make 2 groups. When I make my 2 groups, I always want to make sure I have a plus sign in the middle of the 2 groups, which I do. If there's a subtraction symbol there, I just rewrite it as plus and negative, so I can put a plus sign there. And then I'm going to look for a greatest common factor in the first group. Well, that should be easy to see. That's a 2x. And then we'll look for a greatest common factor in the next group. Should be easy to see. That's 3. And now if I look for a greatest common factor amongst both terms, I notice they both have an x minus 1 in common. And when I factor that out, that leaves me the 2x plus 3. And remember, this was still all equal to 0. I guess I forgot that equals 0. I forgot writing it for a minute. So now that we have this factored, we can apply the 0 product property, setting each equal to 0. So when I do that, I get 1 and -3/2. Is that okay? So that was that long quadratic factoring, right? And again, what the cue was to know you had to do that is when your leading coefficient isn't 1. And we can't turn it into a 1 by doing like taking out a greatest common factor. You know what I mean? Sure. And that was something, again, we talked about a fair amount last year, right? That hopefully rings some bells. Anybody else?
Is that just how you do number 12 as well?
Let me look at 12. Yeah, so once you pull off the x, yes, you'll do the same thing on number 12. So looking for two things that multiply to give you 3 times 15, which is 45, and add to give you 14. So 9 and 5 would be the two numbers you're needing there. And you go through the same process exactly, Peyton. Sure, no problem. Okay. Should we, bless you. We ready to move forward here, folks? All these sneezes and coughs. Okay. So recall, so the last thing we had kind of done was we had kind of built out this idea that we can do this synthetic division process, right? And we noted that the synthetic division process was nice because it was faster than the long division, but still gave us all the same information that we got doing long division. What was the catch, though, with the synthetic division? Why don't we just teach you that and then leave it alone? It doesn't work every time. So for synthetic division to be doable, the divisor has to be a degree 1 polynomial with leading coefficient 1. Okay. So let's just kind of pick up where we were doing. Okay. So the first thing we want to remember is that the remainder theorem basically tells us that f of negative 5 is going to be the same thing as the remainder for this problem. So that's what the remainder theorem is saying. That's how we're going to use the remainder theorem, is that the remainder for this division problem is going to be the same thing as what we get when we evaluate f of negative 5. And what's nice here is that because this division problem involves a degree 1 polynomial with leading coefficient 1, we can just do synthetic division on this. So we don't need to do the long division. So we'll start by setting up our synthetic division. What number is going to go on the outside of our synthetic division bar here? Well, it's going to come from the divisor, which came from the negative 5 here. It's okay there? What are the numbers that are going to go inside my synthetic division bar? Can somebody tell me? Mm-hmm. Mm-hmm. Excellent. Now, Eric, why the 0 there? I don't see a 0 in my polynomial. Why did you put a 0 there? Yeah. So because we went from x to the fourths to x squareds, we skipped the x cubes. So we know that if we're doing synthetic division, we have to include that placeholder 0 there for the x cubed parts. And as Eric stated, if you don't do that, you will get the wrong answer. There's no recovering from missing that. So we definitely want to make sure we're being very careful about those things. Lily.
So how did you find out that f(x) equals x plus 5? What was that g?
No, there's no g's. So this part was all part of the remainder theorem.
Oh.
This is just me kind of filling in how we're using the remainder theorem. Oh. What it boils down to is we're just doing synthetic division on this. Oh. The reason I just wanted to recap what the remainder theorem was saying, which says that what you get when you evaluate a polynomial and when you divide a polynomial in a certain way gives you the same number. Oh. That's all it's saying. Okay. You're welcome. Okay. So when we start our synthetic division, what's our first step? Anybody tell me? Very good. So we just bring the 4 straight down. Excellent. Then what happens next?
Multiply -5.
Great. And where do I write that answer at? Under the 0, we write the product of -5 and 4. And then what do we do? Add down, right? So 0 plus -20 is just -20. So far, so good. Let's keep on rocking and rolling. So -5, and then we just keep repeating that same process that we've described until we're basically run out of spots, right? So -5 times -20 is positive 100. I add down, that gives me 95. -5 times 95 gives me -475. 7 minus -475 is -468. And then, oh, great, googly moogly. -5 times -468 is 2340. So that gives me 2332. Okay. So remember, this piece is the remainder on the far right. So that's what we want. So we'd say in this case, f of -5 is 2,332. Note that's the same thing you would get if you plugged in -5 in like this. Right? Substitution, it's the same process. F of -5 is the same thing, whether you did it using synthetic division like we had just done, or whether you had plugged it in directly. Still getting you the same answer. Now, the directions were specific on this problem, how they wanted us to do it, but it's that same, the same process. Just to reiterate, okay? This brings us, so we have this new division process, right? Synthetic division, which allows us to do the same thing as long division, but it's a little bit more compact. Again, the goal here is still going to be finding these zeros for polynomials. That's what we're trying to do. We're building out towards doing that. So the next tool along this route is called the rational zeros theorem. And it says for a polynomial, f of x equals, and then we're just going to write kind of the general form for a polynomial. Remember, when we're writing this, the a's are just the coefficients on each term of our polynomial. And we're using a subscript there because it's possible that our polynomial has more than 25 terms to it. So we'd run out of like A, B, C, D, E, F, like we'd just run out of letters. Is that okay with everybody? Now, not in this class would we run out of letters, but it's certainly possible for that polynomial to have like 10,000 terms, which is why we're using a subscript on the symbol for our coefficient rather than just using different letters. Is that okay? Okay. This says then any possible rational zero for f of x can be written in the form plus or minus P over Q, where P is a factor of the constant term and Q is a factor of the leading coefficient. Maybe we'll just say AN. So there is there's some vocab in here that's probably worth making sure to emphasize. So when we say rational, what do we mean by rational in this case? Do we mean like the English language rational, like, oh, that's a logical decision you just made? Like math rational.
That either means whole number of positive, I think. Oh, no, it means not imaginary.
Okay, so you're close. So rational numbers are not imaginary, that's true, but anything that's not imaginary is not necessarily rational. The things that are not imaginary are real numbers.
Does it have to not be like infinity or negative infinity as well?
Okay, so those aren't real numbers either, infinity or negative infinity. But you're right, rational numbers can't be that either. So it's just things that can be written as a fraction. So like 1/4, that's a rational number. But so is 4. Why is 4 a rational number? Because you could write it as 4 over 1. Exactly. Is everybody cool? Okay, so what kind of things are not rational numbers other than imaginary things?
They can't be fractions.
Right. An example of that could be, if you think back to your geometry classes, a really one used a lot. a number that used a lot in geometry that can't be written as a fraction? Pi would be an example. Another example of something that could happen here are many radicals are non-rational numbers. For example, like the square root of 2 or the square root of 3 or the square root of 5. All of these things are examples of things that you can't write as fractions. Those kind of numbers that we can't write as fractions we call irrational. Everybody feel okay there? Okay. And when we say 0, what are we talking about here? We're talking about the number 0? No, what are we really talking about here?
Like,
X-intercepts, right? Places where the graph would cross the x-axis, or solutions to f of x equals 0. Those would be, again, we can use those interchangeably. Okay, so let's do some example of how we can use this rational zeros theorem. So here we're asked, what are the possible rational zeros for the polynomial 3x to the fourth plus 4x squared plus 7x minus 4? I'm just going to abbreviate this as PRZ for possible rational zeros. As we'll write that phrase a lot of times, I'm just going to make an abbreviation for it right now. We cool with that abbreviation? Okay. All right. So we know that those are the form P over Q, or plus or minus P over Q, right? And P is going to be factors of the constant term. What's the constant term in our polynomial? That's negative 4. So what are the possible factors of 4? 2, 1, and 4. Usually I like to write them in numeric order, but that's okay. What you've written is certainly totally fine. And then Q is the leading coefficient. What's the leading coefficient? 3. What are our factors of 3? Okay. So our possible rational zeros then would be 2 over 1 plus or minus, 2 over 3, again plus or minus, 1 over 1, 1 over 3, 4 over 1, and 4 over 3. Okay? Is everybody good with that? Now, are all of these going to be solutions, or will all of these be zeros? No. These are just the possible ones. And in fact, at maximum, how many of these could be zeros? 4. because the degree of our polynomial is 4. So at most 4 of these could work. But at minimum, how many could be zeros? 0, right? None of them need to work. We don't know if any of them are going to work right away, or even which ones from the list might work or might not work. Okay? How could we go about figuring out which ones might be good ones to try to see if any of them would work? Now, I will tell you, back in my day when I was a student, this was a tedious process. It has gotten much easier for you as students. Yeah, the calculator is going to do us an enormous favor here. So now, we certainly had calculators when I was a high school student, but everybody didn't have a graphing calculator, which makes just like a world of difference here. So if you go ahead and we graph our polynomial, so in this case, 3x to the 4th plus 4x squared plus 7x minus 4. And I'm going to just graph this on our standard window. So I'm going to just hit Zoom standard. I've been using my calculator for a bunch of other classes, so I think my window's probably all cuckoo crazy. But if you press Zoom and then pick Z standard, that'll just reset your window to usually that sensible -10 to +10. So if I go and I look at my x-intercepts, I see I have 1 here at, it looks like a little bit less than -1, which is probably -4/3. Seems like a good possibility. And then somewhere here, just bigger than 0, but less than 1. So that's probably going to be either +1/3 or -1 or +2/3. I'm not really sure from just looking at it. We'd have to check. Is everybody okay with how I pulled these guesses from my picture? What would we need to do to confirm if these were actually zeros now? Yes. Okay, let's say without the calculator though. We wouldn't plug them into the formula. We'd want to use the synthetic division to see if we get a remainder 0. And the bonus of that, of using the synthetic division to do this, is that we're also going to get the factored form of the polynomial out of that for free as well. So if there are non-real zeros, which in this case, I'm pretty positive there are, we'd be able to ascertain those too. Which is lovely, right? And we'll get into that full process here in a little bit, but I just wanted to kind of preview that. Okay. So if we consider this list of zeros again, right? We get this list of zeros, and that's fairly easy to generate, right? We didn't have to do much to get that. But remember, this is only telling us about rational zeros, right? Things that could be written as fractions. Things that couldn't be written as fractions would not show up in this list. And this list doesn't really give us any indication about what the value of those numbers could be. So what can we use here? So we have another theorem here that we can use. So for a polynomial f of x with leading coefficient, if we divide by x minus k, let's say not if here, say and, we divide by x minus k. We get two possibilities. If k is positive, or I should say non-negative, and every number in the bottom line of your synthetic division is also non-negative, then k is an upper bound for the real zeros of f of x. And then if k is negative and every number in the bottom line, just forgot the word "the" up there, of your synthetic division problem is alternately alternately non-negative and non-positive, then k is an, or I should say a lower bound for the real zeros of f of k. Woof! It's a lot of words, Mr. Kulik. Well, let's just kind of summarize what this is saying, okay? So this pairs with the rational zeros theorem. The rational zeros gives us finitely many possible rational zeros for any polynomial, right? It's saying, okay, if this has a rational zero, it's going to be one of these, and there's always going to be a finite list. You're not going to get infinitely many possibilities. You could get a lot of possibilities, but like it spells out if there's one, this is how we can find it. What this theorem does, it says, okay, the real zeros, though, if you have some irrational thing stuck in there, that's not going to help us. You know, the rational roots theorem is not going to help us find that. What we can do is we can find, okay, well, even if there's an irrational number, it could be no bigger than this and no smaller than this. So this theorem helps us find like an in-between. If we're going to go searching for one of these irrational zeros, this theorem tells us, okay, it can only be between these two values, and then you have a much smaller search space to do this. Let's do an example of kind of how we can use this. So to show every zero for the polynomial f of x, which is yada, 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 lies within the interval from -5 to 4. So to do this, what I need to do is two synthetic divisions. I need to divide f of x by -5. And then I need to divide f of x by +4. Everybody's okay with that? If I think -5 is going to be the lower bound, I'm looking for the parts underneath my synthetic division to be alternately non-negative and then non-positive. So positive, negative, positive, negative. So I have greater than or equal to 0, less than or equal to 0, greater than or equal to 0, less than or equal to 0. So I know -5 is a lower bound for the real zeros for, I should say, of f of x. Is everybody okay with how I kind of analyze that? All right, well, let's do the next one then. So that's 24, that's 49, that's 196. Let's see, 212, and that's, 12, and that's going to be 848, so 833. So again, for this one, for the upper bound, I want all of those guys to be just greater than or equal to 0. So all of them should be non-negative. So non-negative, non-negative, non-negative. So I can conclude 4 is a upper bound for the real zeros of f of x. So if I was looking for an irrational 0, I would know it would have to lie in between these values of -5 and +4. So if I was looking for one, that helps me narrow down where I would need to be looking for. Is that okay with you guys? Now, the thing to keep in mind here about this is that back in the day, like when Mr. Kulik was a student, everybody didn't have a really powerful graphing calculator in their pocket, that you would end up doing like approximation methods for finding these irrational zeros that were pretty tedious and time consuming, but this would be enormously helpful to you. It'd be like, okay, it's between these values and these values, and you just keep like doing substitutions looking for a sign change. And once you found a sign change, you just kind of cut in from each side until you were able to like get down to 2 decimal places, which was like a tremendous hassle, but you know, you could do it. Anyways, is everybody okay with how that theorem is really operating here? Okay. So let's do now like a full example where we can kind of apply what we have so far to actually finding the real zeros. Okay, so we're going to find all the possible zero or real zeros for this f of x. So how many possible zeros can we have? 3, 2, 1, or 0, right? Okay. So of those, possible rational zeros might be everything's the form P over Q, where P is 30 and Q is 6. So my factors of 30 are 1, 2, 3, 5, 6, 10, 15, and 30. Woof! My factors of 6 are 1, 2, 3. So my possible rational zeros are 1 over 1, plus or minus, I guess, plus or minus 1 over 2, plus or minus 1 over 3, then plus or minus, we'll write them this way, I think, 2 over 1, 2 over 2, and then 2 over 3, and then plus or minus 3 over 1, 1 over 3, or I'm sorry, 2 over 3, and then 3 over 3, and we have plus or minus 5 over 1, 5 over 3, oh, I'm sorry. What are we doing here? Right, oh, that should be, goodness gracious, it should be 3 over 2. So we have 5 over 2, and then 5 over 3, and then plus or minus 10 over 1, 10 over 2, which I'm just going to write as 5, and then 10 over 3, and we have 15 over 1, 15 over 2, and then 15 over 3, which I'm just going to write as 5. And then we have 30 over 1, 30 over 2, which is just 15, and then 30 over 3, which is just 10.
Isn't there also a 6?
Did I forget to do the 6s? Great googly moogly, I did, huh? So we have, thank you, Leo, 6 over 1, 6 over 2, which is just 3, and then 6 over 3, which is just 2. Except 6 usually comes before 10. Yuckarooski, so many to check. Well, what I'm going to do next is we're going to go to our graph and take a look at the picture and find a good, or a value from that list here that's going to be a good starting point. Or starting points, plural. In this case, I probably only really need one of them, but that's okay. All right, so I just typed in my function into my y equals. I already reset my window back to -10 to +10, the previous one we graphed, so I don't have to worry about resetting that again. So I'm just going to hit enter. So let's see. So let's see, this is -1, -2, -3, -4, -5. So this one looks like -6. That's on my list. Everybody agree there? That one might be either -1/2 or -2/3 or -1/3. You guys buy that? I don't know really for sure where that is other than it's in between 0 and 1. Everybody's okay there? And then over here, this looks like between 2 and 3. So that could be 2.5. Or it could be, that's probably it, right? Yeah, Leo.
Instead of like writing all the possibilities out first, I check the graph, or is it faster to check the graph first? That's a possibility.
Well, here's the thing. Not every spot on the graph is going to correspond to one of these possibilities, which is a problem. That's why we typically do the rational zeros first. I know. Most of the time there's not, 18 possibilities or whatever to write down. Even though there's really not 18 things on this list, right? Because, we don't really need to write 1 more than once. We don't really need to write 5 more than once. We don't need to write 2 and 3 more than once. We don't need to write, a lot of those things are not really need to be there because we've already listed them once. So the list isn't really as long as it looks. But we do really want to start in that order, because there's certainly a possibility that any of these things that look like they might be fractions might really just be irrational numbers that are really close to a fraction. For example, 3 over 2 is a possibility. The square root of 2 is 1.41, yada, 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 which is awful close to 1.5. I doubt just looking at the picture you'd be able to tell the difference. You know what I mean? Which is why we typically want to start in that reverse. Okay. So we have the numbers that I've highlighted are the ones we'd want to start our synthetic division with. Which one of those do you think looks like the best one to start with? I think there's a correct answer here. I would do the -6. Why would Mr. Kulik do the -6? It's a whole number, so the arithmetic's easier than the fraction. And we're pretty positive that's got to be -6, and there's not a couple of things it could be. So the odds of this getting a non-helpful result are pretty low. And in general, we would want to kind of minimize the number of synthetic divisions we might have to do. Okay. Let's see, that's 78. So that's really nice. What that's telling me now is 6x cubed plus 23x squared minus 83x plus 30 is going to factor down to the x plus 6. And the reason we're getting the x plus 6 is when we divide by -6, we get remainder 0. Times constant x coefficient x squared, 6x squared minus 13x minus 5. Does everybody feel okay in that first step? Now we have two choices here. We can take that piece that I have written in the blue, or highlighted in blue there, the 6x squared minus 13x minus 5, and we could try to factor that by other methods. Now looking at that, is that something we can factor using other methods? Probably, because it's a quadratic, right? And in fact, the method I'd use to do this is exactly the question Peyton asked about in the very beginning of class. Here's a quadratic where the leading coefficient isn't 1, so it's a good question you started with there, Peyton, because it's come up right here. Or the other option would be to continue my synthetic division with these numbers and one of my other zeros. or possible rational zeros. Here, I would probably pick the positive 2.5, since I'm pretty sure that's what that has to be. It can't be something else. Everybody's okay with that? I'd avoid that zeros that we highlighted in green there because there's a couple of different possibilities. So let's see, 12, and then, so that's 15. And then that's 5, so that works out. So again, we get remainder 0. So what that tells us is that 6x, let's say 6x squared minus 13x minus 5 is going to equal, we have to be a little bit careful here. Oh yeah, I think it's okay. So x minus 2.5 times 6x plus 2. Again, since this gave us the 0, that's how we're getting this piece, and that piece gives us that. And then if I take these together, we can say that this factors down to x plus 6, and then this piece factors to that, so times x minus 2.5 times 6x plus 2. So when I set this all equal to 0, to find my zeros, I have the factored form, so I can just set my factors equal to 0. And then we have negative 1/3 here. Now, I want to point out here that if we had stopped at this step, which we could have, we could apply the zero product property here. Right? So we get, again, negative 6 is equal to x. And then the other piece we're left to solve is this quadratic, correct? So one way you could solve this quadratic is by factoring, which we mentioned we could do the same thing that we did at the very start of class with Peyton's question. But what's the other way we can solve a quadratic every single time? Well, that's the one we've already mentioned. There's another way, though. The quadratic formula, which is probably what I would do in this case, since the factoring method I have to use is the long one. So again, the quadratic formula, x equals negative b plus or minus the square root b squared minus 4ac all over 2 times a. So 169 plus 120 over 12. And I think we're out of time here, but you get something out of this. You get the 2.5 and you get the negative 1/3. You'll trust me on that, I assume. For next time, I think we can do the, we should be able to do the worksheet. So I'm going to put that up. And then we should be able to do this one, this one. So I think probably just 32 to 35 and then the worksheet.
See you later, guys.
I have my phone out, but I need it for.
I'll try not to take it away from you right now.